Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So welcome back to our Flyback Converter lecture part 2. So in previous video I already explained the theoretical things about the Flyback Converter. So how it involve adjustment of the buck boost converter. By having a isolation, you can make a flyback converter. And then in the previous video and in part 1 also, I explained about the difference between the transformer of the forward converter and the transformer for flyback converter. So in this part, the second part of flyback converter lecture, we are going to cover the derivation part of all the equation related to the flyback converter, and then we'll look at the problem that occur in flyback converter due to the leakage inductance, and then we will go through the example of flyback converter exercise. Okay, first we will start with the flyback converter analysis. So in this part we will see the circuit operation of flyback converter and how we can come up with equation that relate the input side and the output side of the flyback converter. Okay, basically this is the how the flyback converter will look like with the transformer in place here. So we have the input supply, we have the switch here, and this one is connected to the primary winding. Okay, and then we have the core of the transformer and then connected to the secondary winding. Here we have the diode to ensure the current flow in one direction. We have the capacitor here, output capacitor, and then we have the load side here. So when we translate it into a circuit like this, we represent the transformer, okay, by having this part is the ideal transformer, but we have to, in this analysis we will include the magnetizing inductance Lm, okay, in the analysis. So this is, if you remember from the previous lecture, this is the part where the energy will be stored during the switch turn on and will be transferred to the secondary part during the switch turn off. So we will see the detail of that in the next few slides. Okay, before we proceed with the analysis, these are the assumptions that we make for the analysis. The first one is the output capacitor here. We assume that this is very large. So when this one is very large, what happen is we will get the constant output voltage, okay, at this output side. Okay, you know that there will be a switch on and switch off, and this will impact the voltage here. But due to the use of large capacitor here, the change of voltage here is relatively small, and we can say it is constant. The second assumption is the circuit is operating in steady state mode. So we don't consider, I mean, at initial stage when the switch is just turned on. Initial state, we just consider the analysis based on the steady state after the operation of the circuit is stable. Okay, and this will result in a voltage and current that are periodic, beginning and ending in the same point over a switching period. So this is what you mean by having a steady state. The third one is the duty ratio of the switch. Okay, we mentioned it D, and it being closed for the time of dt and open for the time of 1 minus dt. So in this analysis, the switch will close for dt and for the rest of the time it will 1 minus D, it will open. Okay, and then the last assumption is the switch here and the diode are assumed ideal, so we will not consider any when the switch is turned on, we will not consider any resistance that occur here, or when the switch and the diode is on, we didn't consider the forward resistance, okay, at this point. So we just assume that when the diode is on, I mean this is a close or short circuit at this point. Okay, in this slide I want to explain to you how the current flow in the flyback converter when the switch is closed. So remember that we have switch at this point, but when the switch is closed, we consider it as a short circuit. Okay, the switch will be at this point, so when the switch is closed, we consider it as a short circuit. So what will happen is the current will flow like this into the magnetizing inductance. Okay, come back here. Okay, and then you can ask, okay, how about this this particular loop? Does the current flow through this? Okay, you have to remember, okay, when you deal with the transformer, you have to look at the output side as well. Okay, remember that in original circuit, the diode is like this. Okay, so remember when we have the current going into the dot here, the dot notation at the secondary side. Remember the dot notation, when current go into the dot at one side, it will go through the other dot, go out from the other dot at the output side. So the current should flow like this. Okay, but remember we have the diode here. Okay, because we have the diode here, the current cannot flow. So at this point, we know that the current cannot flow at the secondary port because we have the diode that block the flow of current. So there will be no current at this point. Okay, so this one is open circuit and no current will flow during this time. So that the current flow when we have the switch closed. So how about when we have the switch open? Okay, remember that we have this one is open, so there will be no current can flow at this loop. Okay, remember from now we have the, okay, when the switch is closed, before that this one is positive and this one is negative. So when we remove the supply from the okay, remove the supply, because we have the open circuit here, we remove the supply from this inductor. What happened in the inductor is it will change the polarity of the inductor. So this one will be positive, this one will be negative. So when this one is positive, the current will flow like this. Okay, in this loop. Okay, so remember that, okay, when the current flow like this, the current flow out from the dot side here. So here what will happen is the current will flow into the dot. So the direction of current is like this. Okay, remember that the diode direction is like this, so it can follow the flow of current. So the current will flow like this, and then also at the second loop like this. Okay, and we'll complete the loop. So this is how the current flow when the switch is open. Okay, remember this is the second time when we have the switch closed and then the switch open, and then after that the switch will be closed again. So remember, when the switch is open, we have the current flow like this, mean that the voltage at the capacitor is positive, negative. So imagine that when the switch is closed again for the second time, Okay, what will happen is we have the same one at the input side, but at the output side, okay, remember we have the current flow like this at the capacitor, and when we remove the source from this capacitor, the polarity will be maintained positive negative, but the current will flow, okay, out from the same direction it come in. So let's say before this it come to this slide, this capacitor at this direction. When we remove the source, it will flow out from the same direction it come in. Okay, so the flow of current is like this. Okay, so this is how the current at the secondary side when the switch is closed. Okay, in this slide we are going to see the equation related to the source side, the input side here, and the output side at this point. Okay, first we are going to see the V1. V1 is the voltage across the primary winding at this point. Okay, and then the voltage here is equal to Vs, because this point is connected to this point and then connected to Vs, and also this point connected here to the Vs. So V1 is equal to Vs and equals to the voltage across the magnetizing inductance here. Okay, we know that the voltage across the magnetizing inductance, okay, when we have the inductor, the voltage across inductor is equals to the inductance itself multiplied by the rate of change of the current through the inductor divided by dt. Okay, di over dt. Okay, now we can rearrange the equation here. You can see this one we can move to the other side, become Vs over Lm here, and then we remain with equation dilm over dt. Okay, from this equation, okay, I try to write here. We have, okay, at this point we have Vs over Lm dilm over dt. Okay, and then when we want to change to this Lm, we move here, Vs over Lm equals to dilm over dt. Okay, so this part is this one. Okay, so dilm over dt equals to delta ilm over delta t, so equals to delta ilm over dt. So this point, the delta ilm is this one, the difference between this point to this point. So the value here is delta ilm, and dt is this one. Okay, so the time from this to this, so this is dt. So when we have the delta ilm when it's closed is equals to, when you solve this equation, you will get Vs. Okay, when you want to just to find the delta ilm, you move this dt to this side, so the equation become Vs multiplied by dt divided by, okay, you have to remove this point, this dt here to this point, and the equation become Vs dt divided by Lm. So this is the equation for delta Ilm. The delta Ilm, remember, this is this one minus this one. Okay, at this point minus this point. So the equation is this one. And then now we look at the output side. For the output side, V2 is equal to V1 N2 over N1. So the voltage here, you have to use the transformer voltage equation. V2 equals to V1 N2 over N1 equals to, because V1 is equal to Vs, Vs N2 over N1. So now the voltage Vd is the voltage across the diode here. Okay, and to find that, you have to do the KVL around this loop. Okay, you have to do KVL around this loop. So here we have the V out V out at this point. Okay, the voltage here, and the same is the voltage across the capacitor. So this is the V out, and then we have the VD here. We have the VD, and then at this point we have the V2. V2 is basically this one lah. So when you do the KVL around this loop, you will get VD equals to negative VD equals to negative V out minus Vs N2 over N1. Okay. And how about the current? The current that flow through the I2, because we know that the diode here will block the current, so there will be no current during the switch on. And then for I1 is the current that flow here, so this one is also 0 because there is no current. All the current at the source side will go through the magnetizing inductance. Okay, now we will see what will happen in the flyback converter when the switch is open and what are the equation related to it. Okay, during the switch open, you know that there will be no current flow at this because this switch is already open, and we know that the current will flow this way. Okay, in the primary circuit, the current will go like this. Okay, and then for the secondary circuit, the current will go like this. Okay, so we know that much. And then the V2, okay, the voltage across the V2 here will be equals to negative V out, because V out we measure at this way, and V2 is equals to, okay, we measure V2 from this side, so V2 will be equals to negative V out. Okay, and then we have V1, okay, the voltage across the primary winding here is equal to V2 multiplied by N1 over N2. This is the transformer equation, equals to negative V out multiplied by N1 over N2. So the voltage across V1 here will be equals to negative V out multiplied by N1 over N2. Okay, now we have V1, the voltage across V1 here, it is also connected to this magnetizing inductance. This one is connected to this point is connected here, so the voltage across this must be the same with this. So we have the voltage across the magnetizing inductance here is Lm dilm over dt will be equals to V1, and this one is equal to negative V out multiplied by N1 over N2. Okay, and like previous one, we want to know about this one, so we will move the Lm to this side. Okay, Lm we will move to this side, so the remaining one is dilm over dt equals to delta ilm over delta t. So in this point, in this during the switch open, the delta t will be from here. Okay, the delta t will be from here to here, so this is the delta t during the switch open. And how about the dilm? Delta ilm is the same, so the point from this point to this point. Okay, so from this point to this point, so they change the difference between this one, so this is the delta ilm. Okay, so when we want to find the delta ilm, only we have to move the delta t part to the other side. So that's why we have the overall equation for delta ilm. Okay, this one is equal to negative negative V out 1 minus dt over Lm and multiplied by N1 over N2. So this is the equation for delta Lm when the switch is open. Okay, here are other parameters that we can find in the flyback converter when the switch is open. Here we have the ID, the current across the diode will be equals to the Ilm, the current that flow through this primary side here, multiplied by N1 over N2. So it relates with the transformer equation. And then we have the V switch, the voltage across the switch here. You have to use the Kirchhoff voltage law in this loop, okay, to get the V switch. So we try to look at that KVL. Here we have, let's say we do the KVL across this loop. So we will have negative Vs, and then here we have the V1 here. This is positive, negative. We have plus V1, and here we have plus V switch will be equals to 0. And then we want to find the V switch. So V switch equals to we have Vs minus V1. Okay, and then we have Vs minus V1 is equals to negative V out N1 over N2. So and out we will get Vs plus V out N1 over N2. So we get the equation here. Okay, and then for the output current here, the IR, the current across here, is equal to V out over R, and the current that go through this capacitor here is equals to ID minus IR. Okay, the current ID is the current coming from the primary side, which is equal to ILM N1 over N2 minus V out over R. V out over R is the load current here. Okay. Okay, now after we already have the equation for the delta ILM during the switch close, you get this value, and the delta ILM when the switch is open, you get this value. We want to find the relation between the output voltage and the input voltage by having the assumption of steady state equivalent or steady state balance between the input and output. We know that the delta ILM, the distance between here to here, will be the same as the distance between this point to this point. The value of delta ILM is the same. So we can have this equation, delta ILM close plus the delta ILM during its open will be equals to 0. So this is the steady state balance equation that we can use to relate the output and input voltage. Okay, and then from this equation we just plug in the value that we have, Vs dt minus the delta ILM when the switch is open equals to 0. So when we want to try to solve it, we have, okay, when we can use the equation Vs dt over Lm will be equals to V out 1 minus d t over Lm N1 over N2. Okay, so here what we can cancel out is this one, we can cancel out, the t we can cancel out. So if we want to solve for V out is equals to Vs okay, d, this one you bring to this side, become 1 minus d. Okay, and then when N1 over N2 you want to bring to the other side, it will become N2 over N1. So that's why you got this equation. So V out equals to Vs d over 1 minus d multiplied by N2 over N1. Now we want to find more equation that we have in this flyback converter, and for that we need to make some assumption that all the components are ideal. So by saying this, we are assuming that the input power is equal to the output power. So we have the input power Vs Is, okay, the voltage source here multiplied by the current is equal to the voltage at this point, V out square divided by R. Okay, for the Is, okay, you have to know that Is is only, Is will be the same with the ILM during the switch turn on. So you know that this is the waveform for ILM during the complete cycle, when the switch is on and when the switch is off. Is is only occur at this point, at this part here, when the switch is on. So when we want to relate the Is and Im equation, it will be like this lah. So we have the Is here is basically the ILM, but only at this portion. So that's why we get the equation here, Is equals to ILM, but only for the portion from dt over t. T is overall here, and the dt is, we want to highlight the portion where the Is occur. So at this, so this is dt over t. So Is will be equals to ILM dt over t, and then we can cancel out the t part, and we will get ILM d. So Is will be equals to ILM d, and then we will substitute back this Is equals to ILM d. We will substitute back in this equation. You will get Vs ILM d equals to V out square over R, and then we will only take this equation, and all other will be moved to this side. ILM will be equals to V out square over Vs dr. Okay, so from here you can move the component d and Vs, and it will become this equation. Okay, now we already get the value of ILM equals to V out square over Vs dr. So you can use this equation if you have the value of output voltage and the input voltage. Okay, straight away you can calculate the value of ILM. Okay, to proceed further, we can replace the V out, okay, in this equation with the one that we already obtained before this, that relate the input and output voltage. So when we replace this, it will become V out square, all of this square, divided by Vs dr. Okay, so when you make everything square and you cancel out all of the equation that is common, the remaining will be ILM equals to Vs d 1 minus d square r, and then multiplied by n2 over n1 square. Okay, so we can try to do that here. If we have the ILM equals to, we have Vs d over 1 minus d, okay, and 2 over n1. Okay, when you square everything, what it means is this one will be squared, d will be squared, 1 minus d will be squared, Vs will be squared, right? So divide by Vs dr. Okay, so this one can be cancelled out, the d1 will be cancelled with this one, and then okay, the remaining equation will be ILM equals to Vs d over 1 minus d square r, and then you have n2 over n1 squared. Okay, sorry, this is n1. Okay, so this one ILM will become like this. So you can use this equation if you don't know the value of output voltage. Okay? We don't have the value of V out. We can use the VS here. Okay, and then if you see furthermore this one, if you take all the Vs d over 1 minus d n2 over n1, you factor out this. You factor out this from here. So it means that you want to replace the Vs d 1 minus d n2 over n1 with V out. You can get this equation. ILM equals to V out 1 minus d r n2 over n1. Okay, so this one you can use this equation if you only know the value of. Okay, you can use this equation if you only know the value of V out and you don't have the value of Vs. Okay, so if you have the both of the value of V out and Vs, you can use this equation. If you only know the Vs, you don't know the value of V out, you can use this equation to find ILM. And for this you can use this equation if you don't know the value of Vs. You can use this equation. Okay, from previous slide we already find the equation for ILM. Okay, ILM, if you have the inductor current waveform here, the ILM that you calculate in the previous equation, the ILM here is, if you want to draw, is average voltage of inductor current here. Okay, it's straight line. Okay, and then the one that we want to find now is the ILM max. This is the value at this point. Okay, if you have the value here, this is ILM max, and then at this point we have ILM min. Okay, so if you want to find the value of ILM max, this is just the ILM plus the delta ILM. Delta ILM is the value from here to here, divide by 2. So you want to know half of it, half of the value here. So this one is the delta ILM. Okay, so divide by 2. Okay, so ILM max equals to ILM, all of this ILM plus the delta ILM divide by 2. Okay, and if you want to find the ILM mean, it's just the ILM minus the delta ILM divide by 2. You have half of it here, and then you just this equation minus this equation. Okay, this is how you want to differentiate the operation mode of the flyback converter. For CCM, the ILM max, the ILM min, the value down here will never reach 0. So we'll have some value here. Okay, never reach 0. So that one we will call it the CCM operation. But for boundary operation, it will touch the 0. Okay, during the time equals to t. So for the boundary, it should look something like this. Okay, let's say we have here, and then it will go down until it reach 0, and then we'll go up again, and then we'll go down until it hit 0. So this is the boundary operation. Okay, in this slide we want to find the value of LM min. Okay, this is the value that we want to find, so that we can ensure that our flyback converter is operate in the CCM mode. Okay, so to find that, we have to find at the boundary condition ILM min equals to 0. So we already have the equation for ILM min. Okay, these are the equation equals to 0, and then okay, this one you can move this one to this side. This one equals to VS dt over 2 LM, and T here we can replace by 1 over f. Okay, and then when we solve the Lm here, this is considered the minimum Lm. Okay, the minimum inductance that we can use equals to 1 minus d square r over 2f multiplied by n1 over n2 square. Okay, so this is the minimum value of Lm that we have to use. Okay, so if you can see from this equation, okay, if we have value here which is larger than this value, so it means that this term will become smaller. Let's say this one is 2, when you make it double, become 4, so this term will be smaller because this value divided by bigger value, this term will become smaller. So you know, when this fixed value minus the term that is already become smaller compared to the previous one, so you know that ILM mean will not reach 0. Okay, so now we already find the condition when it is 0, so the value that we must take, okay, when we already calculate the value of LM mean, we have to ensure that our the chosen value of the magnetizing inductance here must be bigger than the value that we calculate at this point. Okay, so we have to make sure that our value of the magnetizing inductance that we choose here should be bigger than this value to ensure that our circuit is operating in CCM mode. Okay, the output ripple voltage for the flyback converter will be the same with the output ripple voltage for the buck boost converter, because the output configuration of both converter are the same, and voltage ripple due to the equivalent series resistance will be equals to the current ripple, the maximum current ripple of the capacitor current multiplied by the RC, okay, the resistance across the capacitance. Okay, and this delta IC will be equals to the Ilm Max, the maximum current that come to the secondary winding here, or the secondary circuit here. Okay, here we will refresh back the shape of the waveform for the ILM. Okay, when the switch is closed, the current will flow like this, and then when the switch is open, it will go down like this. So this is for CCM operation. Okay, for CCM operation as well, this is the IS, the input current here. Remember that the input current will be the same with the ILM during the switch turn on. Okay, but after the switch turn off, we know that there will be no more IS at this point because the switch is already open, so the current will become 0 for IS. Okay, but when the switch is turned back on, the current will follow the ILM. Okay, now is the current for ID, the diode current. So you know that during the switch close, the current that flow to ILM only go this way. Okay, and then there will be no current during this time. So during this period, the ID is 0, but when the switch is open, we know that the current that flow here will be the same with the ILM. Okay, the shape will be the same with ILM, but here we know that it will have to be multiplied by the ratio of N1 over N2. Now we will look at the current that flow through the capacitor here. We know that during the switch on time, okay, during this switch on time, the current will be supplied to the load from the capacitor. So the current will flow like this. Okay, and the value of the current here will be negative V out over R. So this is the output current. Okay, and then we have the minus because the original direction of IC is supposed to be this way, but when it's supplying to the load, it will move this way. So that's why we have negative V out over R here. Okay, and then during the switch open, okay, during the switch open, the current will come from this ILM here. It will come here. Okay, and then at this point, the current will follow the shape of the ILM. Okay, but you have to multiply this N1 over N2. Okay, so it will follow the shape of ILM during the switch open time. Okay, this is the voltage for the V1, which is the voltage at the primary winding. We have during the switch turn on, this voltage will be equals to Vs. Okay, that's why we can see here Vs. And then during the switch turn off, the voltage here will be equals to negative V out N1 over N2 at this point. Okay, this is the magnetizing current for flyback under DCM mode. Okay, so we can see that during the switch on time, the current will increase from 0 here, okay, until some value. We have the Ilm Max here, and then after that, during the switch off time, the current will reduce until 0. Okay, so at this time the current will remain 0. So you can see that the current drop at 0 before the complete of the switching period. So this is what happened with the ILM when it is under DCM mode. We are now looking at the input current for the flyback converter under the DCM mode, and you can see that the current will increase from 0 as well, and it will reach some value here, and the value here, it is the same with the value of Ilm Max or the Ilm during the switch turn on. Okay, so remember when we derive the equation for flyback converter, during the switch on time, this is the value of delta IL. So we have the maximum value here, the same as that. After that, the value will straight away drop to 0 because the switch is closed, and then it will reach the next cycle during the, this is the T, so it will increase again at this point. And for the ID, which is the diode current, during the switch close time, it will be 0 because the current cannot flow due to the this diode is blocking the current. But during the switch open, okay, during the switch open time, we can see that the value here, the maximum value, is the value of delta IL multiplied by N1 over N2, and then it will reduce to 0 before even reaching the complete switching period. Okay, for the capacitor current during the DCM mode, when the switch is closed, the current that flow here will be negative I out. Okay, the current that flow through this capacitor will be negative I out because it is supplying the I out from the capacitor. Okay, and then during the switch open time, the value here will be okay, the value at the peak here will be the ID. Okay, ID minus I out. So it will follow the same shape of reduction with the ID. Okay, now we continue with the V1. V1 is the voltage across the primary winding. So we know that during the switch close, it will be the same with the Vs because it's connected to the Vs. Okay, during the switch open time, okay, this value of voltage will come from this side. I mean, it is the value of negative V out multiplied by N1 over N2. So this winding will experience the voltage negative V out multiplied by N1 over N2. Okay, but after the current, okay, after the current ID reach 0, so what will happen is the voltage experienced by V1 will be 0. Okay, and it have to wait until the next switching cycle when the switch is turned on again, so it will receive the voltage from Vs here. Okay, this is the waveform for the secondary winding during the DCM mode. When the switch is closed, okay, when the switch is closed like this, the voltage here will be the same as the negative Vs multiplied by N2 over N1. Okay, during this time, the V1 will experience Vs. Okay, but for the V2, you have to multiply by using the transformer equation that relate N1 and N2 here. Okay, during the switch open, the voltage that occur around this port will be the same as V out. The maximum value here will be V out. Okay, and then after some time when the diode current reach 0, the diode here will be reverse bias, and then at this point the voltage experienced by the secondary winding will be 0. Okay, before this we know that we can define the DCM and CCM using the inductor current, okay, the magnetizing current, but we can also define or see whether the circuit is operating in DCM or CCM by looking at the IS, which is the input current, and ID, the diode current. Okay, so for DCM you can see that this from here 0 to T switch is one whole complete period of switching period, so the current will increase and then drop to 0, and for the ID it will increase, here will be 0, and then when the switch is off, the value of diode current will reach 0 before the complete switching period. Okay, and then for the boundary condition, the diode current will reach 0 exactly at the switching period here, okay, at the switching time here. And then for the CCM, you can see a trapezoidal shape here. Okay, the current will not increase from 0. Okay, IS will increase from some value to the maximum value and then suddenly drop to 0. Okay, and then this one for CCM, we can look at the ID. ID will also reduce, but when it reach the switching time here, it will straight away go to 0. So the shape of the IS and ID in CCM will be trapezoidal, while for DCM it will be triangle like this, and with the same with the boundary condition, but the boundary the current of the diode will reach 0 exactly at the switching time here. So now we are looking at the flyback converter application. So flyback converter is a common converter circuit used in daily, household and consumer electronics such as TV, printer, PCs, monitors, battery chargers. Okay, for let's say for the now we are using solar PV, so the charger circuit for solar PV also can use the flyback converter. And then we have the AC adapter, the one that you want to convert, okay, from AC to DC. Okay, we can find the flyback converter as well. Okay, now we are looking at the comparison between the DCM and CCM. Okay, for the same rating here, if you can see here, 40 watt, and then this is also 40 watt switch mode power supply using DCM mode, and this one using CCM. Okay, the blue one using CCM. You can see that for CCM, the peak-to-peak variation is small for the current. Okay, the maximum current is 1.1 and the minimum is 0.6. Okay, and the switching loss will be lower here, which is 1.1 watt. For the DCM, okay, although it starts from 0, the peak will reach 1.7. Okay, and the switching loss is 1.3 watt. Okay, so the disadvantage of having the DCM is it will occur higher IR square loss because the current that okay, you can see even for the IM current here, the value is higher, so the I square R losses will be bigger. Okay, and then for the DCM, we require a bigger input filter to reduce the electromagnetic interference. But the advantage is we can have a lower cost for the secondary side rectifier diode, because the diode here it doesn't have to I mean the stress for the diode is lesser, so we can choose a lower cost diode because the current will reach 0 and then it will turn back on. Okay, for the CCM, it will have lower conduction losses. Okay, and then the smaller input filter required to reduce the EMI. And then for the diode requirement, it requires a fast recovery diode to accommodate for the switching action here. Okay, so that's the comparison between the DCM versus the CCM for flyback. Okay, now we will look at the effect of the leakage inductance in the flyback converter. If you still can remember, for the forward converter, the leakage inductance will reduce the output voltage at the secondary side of the forward converter. Okay, but for the flyback converter, the effect is a little bit different. Okay, you can see this is the voltage across the switch. Okay, the VDS across the switch. When the switch is turned on here, when the switch is turned on, the value will be 0 across the switch. Okay, and then when the switch is turned off, okay, the value or the voltage experienced by the switch will be E in plus NP over NS multiplied by V out. So this is the maximum value of the switch or the rating of the MOSFET that the designer will choose. But due to the leakage inductance, okay, we can see that okay, due to the non-ideal coupling between the primary and the secondary winding, so this will occur the leakage inductance in the winding. So when the winding is energized during the switch turn on, there are some energy trapped in the leakage inductor. Okay, so this leakage plug need to be dissipated using the external circuit. So okay, to ensure that this energy is dissipated correctly. So if this energy is not dissipated, it will cause a large voltage spike across the winding, and the spike, let's say the rating is 400, and then when the spike occur, the voltage can reach 500 or 600 volt, and this will damage the MOSFET or the switch. Okay, so the leakage inductance spike will look like this. So if it is not dissipated correctly, so this extra voltage here will damage the MOSFET. Okay, now that we know that the leakage inductance have some bad impact to our MOSFET here, okay, so we need to have some protective equipment or protective circuit, and this is called the Rcd Clamp, okay, or Rcd snubber. So the concept here is we want to transfer the energy, excess energy in the leakage inductance to the capacitor here, and then eventually the energy inside the capacitor will be dissipated through this snubber resistor in the term of heat. Okay, so the process involved is when we have the leakage inductance, this will affect the VDS here. If VDS here is more than the normal value that is supposed to be, then it will turn on this diode. Okay, and all the extra energy will be transferred to this capacitor, and then and this resistor, and then the energy inside the capacitor will be discharged through this snubber circuit. Okay, this is the final part for this lecture. In this, I want to explain to you about the parasitics component or parasitic capacitance and inductance that can occur in a circuit. Okay, when we say parasitic, by the name itself, you know that this is some unwanted capacitance or the stray capacitance. So this is not a physical component, a capacitor that you put in the circuit. So this is the capacitance that exists. Okay, the capacitance exists between the part of electronic component due to the short distance between each other. So imagine that if you have a circuit board, and on the circuit board you will place several components. Let's say the capacitor beside the resistor. If you put the capacitor and resistor close enough, there will be some, we call it imaginary parasitic capacitance between both of the component. Okay, and it can occur in the inductor, diode, and transistor. And due to this parasitic capacitance, sometimes it can cause the behavior of the circuit differ from the ideal condition. So let's say when we design something, we expect it to be this way, and due to parasitic capacitance, our circuit didn't behave like the one that we want. So if something that we design and it didn't work, so some, or we can say some of the cause may be due to the parasitic capacitance. And the second one is the parasitic inductance, also known as a stray inductance. So this one is produced by having a long wire of component. Okay, so if you have a wire or conductor here which is long enough, okay, so it can result in a parasitic inductance. You know that in circuit board usually we want the component to be as close as possible to the circuit board. Okay, this is to minimize the, okay, let's say for this capacitor here, we want it to be as close as possible to the board, because we want to avoid having a long wire here or the long terminal here. So we want to make it as short as possible to reduce the effect of parasitic inductance. Okay, and the parasitic inductance, it can result in disruption of normal current flow within a circuit. Okay, so for the flyback converter, these are the parasitic elements that can occur in the circuit, and these are the name of the parasitic capacitance that you can find in the flyback converter. Okay, now we are at the end of the second part of the flyback converter lecture. So in next part for the flyback converter, we will discuss and I will show you the example related to the flyback converter. Okay, so the first part and the second part is just a theoretical explanation about the flyback converter, and the next part will be the example regarding the flyback converter. So thank you for your attention, and I hope you can get something from this lecture, and see you again next time. Assalamualaikum warahmatullahi wabarakatuh.